We have a homework 4 due on Tuesday. So what is the rule for quizzes? Any? So we are submitting it in the mailbox. So I can, on Tuesday. Oh, okay. So all the quizzes are due on Tuesday. The whole week quizzes are due on Tuesday. That's, oh, what if there is a homework due on Friday? On Fridays. Even then that will be due on Tuesday? Okay. But I will put the dates as if it is Friday or Monday, and then no, I think that will be too confusing. It's hard. So you want all the homeworks and quizzes to be due on Tuesday. That's the point. Is that possible, Ken?
Yeah, I guess that works. Yeah. So if we have a quiz Monday, it'll be due Tuesday. If we have a quiz Friday and Monday, both will be
Due Tuesday.
Okay.
Quizzes seems okay. Homework, sometimes I'll make it due Thursday also, maybe. I don't know. It might be necessary in the sense if we are to postpone from Tuesday, it cannot go all the way next week. That might do off the chart. So yeah, homework, I'll try to make it on Tuesdays, but give me some leverage there. Quizzes, I think, seems reasonable. That's always on Tuesdays. Okay, yeah, that might be okay. Confusing to me. So we have and yeah, more importantly, midterm 1 on 1 week from today. 1 week. Oh, 1 week. Begin class. And from this point on, we cannot change the date cannot change the date to a great extent. If there's a natural calamity, we cannot help. But I mentioned that because we have one more student, Rob, probably you guys have met him. He has taken a holiday he teaches in a university. So he has taken a holiday. So I think we should respect that and not change. As far as possible, again, if necessary. Decide on this. Okay. And we started introducing the complex number. We introduced the idea of addition, subtraction, even multiplication and division of complex numbers. And we would now like to have a rough idea of having a visualization of a complex number. By now, it is pretty straightforward. Everyone sees the complex number on a plane, right? On an XY plane. That's exactly what we want to do. But I want to stress on that because that's historically, that interpretation was not available for almost 300 years. I think we are talking about 1550s to 1800. 1550 was the first time when complex number, at least in written literature, showed up in solving a cubic root, and no one had enough trust on it, and it was not very easy to work with it, primarily because you didn't have a visual picture of what it is. And suddenly in 1800, this interpretation was given that this can be seen as a point on a complex plane, and suddenly everything got very clear, and there was a lot of progress on it. In fact, within 50 years after that, Cauchy proved almost everything that was necessary in complex numbers. It was, and you will see that there's a lot of things related to Cauchy in complex numbers. So one person pretty much did a lot of contributed significantly to it. So the idea here is our Venn diagram. So if we have a complex number, z equal to x plus iy, it's understood that x and y are real. Z is the complex number. That is a simple. In fact, once we have studied polar coordinates, it is exactly that. We often say this is a complex plane by writing like this. That just seems to be a way to point that out. So that's your x, that's your y. This is also called the real part of z, whatever is not with the I. It's a real part of z. This is the imaginary part of z. And if you remove the I, so first subtract the x out, and then you remove the I, and that's your y. And xy in this way has a, if you say this is your 0, that's your x comma y. That's your z, let's say. It's clearly, that's your x, and that's your y. If I make this rectangle out of that, that's also y, and that's also x. This length, that's forms the right triangle, and immediately we know that this is x squared plus y squared. Right? So this we will say, and that we have already seen. What is x squared plus y squared? How can we, under what operation can you get x squared plus y squared? And we saw that that's nothing but z star. That's a straightforward thing again. And this we will often write it as magnitude of z squared. So that's all clear and obvious as of now. And like in vectors you can think of a vector as xn is made up of x and y component, or you can think of it as a magnitude and a direction. Right? So this is your magnitude, or the absolute value of the complex number. And now you can, if you want to specify this point, you would say it is so many angles, so much of angles with respect to the x-axis, right? That's what in two-dimensional vectors you will say is a direction, right? And this we will say is angle theta. So immediately using our geometry of a right triangle, you would say x is equal to yeah, now I should also, yeah, we will also call this magnitude of z squared as r squared. Again, having polar coordinates in mind, it's good to represent that as r. So let me here explicitly say that. So that's r. So using the geometry of this right triangle, we know that x over r is cosine theta. So that's x is r cosine theta. And y is r sine. Those two come out immediately. And what else can we say? There's of course x squared plus y squared is equal to r squared. And one can also talk about angle theta itself in terms of, so this is x and y in terms of r and cosine theta. I can say r is equal to x squared plus y squared. And then suddenly the square root comes in, and we will say that this is the positive square root. So this is positive. So we're specifying that that's a positive square root. And the angle theta is here tangent inverse of y over x. And that's a little a bit of an issue in the sense that this is multi-valued. Tangent theta is multi-valued in the sense that whether it is this or if it is somewhere at some point here, they will have exactly the same theta. So this requires some cap. And that's exactly the confusion one arises. But in this case, it is too trivial. You can actually visualize it. But if you didn't have this picture, then it is a little hard to know which part it is. But again, if you have the algebra, if you know this form, you can say, oh, this is in that quadrant. If I'm in the third quadrant, I will say that I have to add a 5 to it, right? So you might have seen this in when you do kinematics, I think, or various places. The tangent inverse is multi-value. Again, why is that? Why does that happen? So tangent theta is it's like this. Right? So this is 0. That's your 2 pi. That's your 2 pi, right? 0 pi by 2, no 3 pi by 2. So it's somewhere here. So that's your 2 pi. So there's one, if you have this value, it is unique. But if you have this value, it can be either this or this. The inverse function for tangent theta is not unique. Keep that in mind. We'll come back to that. This will be around with us all through when you're doing complex numbers. But this picture, let's use this to understand multiplication a little bit. Let's say, let's see, should I do multiplication right away or no, before that. So we have this x plus iy. So let's say, I'm going to put this video. So we have to substitute this out there. So v is equal to r is x is r cosine theta plus I y, which is r sine theta. That should be straightforward. R is common, so one can factor this out. And when you get this structure. Now at this point, remember we are getting a cosine of an angle and multiplied by an I times cosine of an angle. At this point, one can also ask, oh, is this equal to something? And that's not obvious when you first time see it, but you are probably aware of it. It is very popularized a lot. But let's try to see this a little more carefully. We would like to know, what do we mean? What do we understand by the cosine of a function? That is this. Yeah. Okay. What do we understand by cosine of a function? Like in general, how do we define cosine of x? Like we typically say that given a value of x, that is a number it spits out. So how do we get that? So is the question clear? Very weird or not very clarified? So cosine of x, how do you define this? From the very scratch, if you were to say.
In the unit circle?
On a unit circle, okay. Make it more precise. Like I give you cosine of, let's say, it has to be between 0 and 2 pi, right? Let's say cosine of 30 degrees, let's say, pi over 6. That's a number. So cosine of 1, let's say. How do you go about evaluating? We of course put it in a calculator, or that is a whole handbook these days. No number is spit out by that. How would you go about checking it, let's say?
To find the x value of a unit circle.
Yeah, unit circle. Okay, let's see. So That's correct. That's a geometrical picture again. So you would say, yeah, tell this again. I'm
So
trying to build it.
where the x axis would be the cosine.
X will be the cosine. Okay. So this, so unit circle. So, oh, I see what
And
you're
then
saying.
yeah,
So you would say, take the value angle theta, and this length is your, so this is angle theta, that's 1. So r cosine theta, right? So this is x, let's say x is by construction cosine theta, that's exactly like this here. Good point. Okay. That's a good definition. I would say this is a geometric definition. How do you teach the computer to evaluate this? Like, I think what you're saying is that measure this distance. Correct? That's correct. And geometrically, often you can get precise numbers for this. But if you want, let's say, cosine of 1.372, probably this is not, I'm not saying this is wrong at all. This is great. But I'm trying to motivate something from my, something that I have in mind. Typically, all these functions that we think of, the best way to see them is as a series. And that's a unique, every function has a unique series associated with it. And you can, more terms you keep in, especially for x smaller less than 1, you can get as precise as you want. So what I'm trying to point out is that there is a power series for every function. So this is 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial and so on. And this is the way you want to see a function. In fact, every function that you will see around, as you proceed, you will get more and more sophisticated. As of now, or at least in the first few functions that you learn is exponential, natural log, sine and cosine and so on. Very few of them. Later on, you will start seeing a bunch of them, like special functions, especially what they're called, which cannot be written in terms of any of these functions that we study early. And the best way to see them is as a series. And they will all, every function has a unique series to itself, even in whatever form they are. That's the way you want to look at it. So that's just a suggestion. So similarly, sine of x is equal to, it starts from x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial and so on. There is also an associated function which is connected, as we will see that this is very closely connected. But when we first time see it, at least as we are studying, or it's possible that you will see this as independent functions. So this is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And you roughly see that, oh, that is this x squared, x cubed all showing up here, but they are coming with different signs, right? So one should be careful about that. But now you could ask, what if I change? Like, let's start with exponential, or let's say cosine, right? What is cosine of I of x, right? When we started, especially in this circular picture, picture of the circle that you drew, there x is a real number, right? That's the length of a quantity. You don't expect it to be complex, or it's not very obvious what cosine of a complex angle means, right? It is started out here. But here it is clear, because here this involves normal operations, addition, right? And powers. Like, we know, if we know how to multiply, if we have defined multiplication, we know how to evaluate each of these terms. If we know addition, we add this up. In the geometrical picture that Ken pointed out, I'm not saying it's right or wrong, that's not the point. I'm trying to say that it might be difficult to realize, oh, I don't know how to do this. right? You'll be stuck there. So it's a little useful in that context, but having said that, it should go together. I'm not trying to say that one is about, like, geometry is always significantly necessary, especially when you're in an unknown territory. Like, you don't know what this is all about, and if you have a lot of equations, then a picture helps a lot. So in that sense, here in this expression, cosine of ix is well defined. We can do that, right? If once we have, we know how I works with other numbers, we know how to do this. So this is, just put it in, right? So this is 1 plus, no, minus I of x the whole square over 2 factorial plus I of x over 4 factorial, and so on. And one learns that, I think we should change this. And one learns that this is I, there is an I square here showing up. I square is -1. So this changes sign. In fact, it changes sign only in this case. Here it is I raised to 4. It doesn't change sign, it stays the same. And this I will again change sign. Let me write that. So it's x raised to 6 over, no, yeah, 6 factorial and plus 1. So all of them come with a positive sign, if you want. And similarly for sine of x. Sine of I of x. So that's I of x minus I of x cubed over 3 factorial plus I of x raised to 5 over 5 factorial, and there's a minus that keeps good. This time I remains as it is, so I keep this. Here there is I cube we know is minus I. And this one is I. Each term has an I remaining. And the best way I can say is that I take an I common, and this is x plus x cubed over 3 factorial plus x raised to 5 over 5 factorial. And this, yeah, and this is plus, and so on. Right. Again, just because these are involving simple operations of multiplication and division, we could extend this definition immediately to the complex plane. And so now we know how to evaluate the sign of ix. In fact, we can even do it for any complex number because we know how to do squares of a complex number and so on. But this now is very tempting to see that, oh, so this is this plus this, especially if I were to put an I, if I were to remove this x, this seems to be either exponential, right? So let's try to see that. So if I were to add these two, it seems to suggest that the sign of I of x plus sine of I of x over I, right? That's equal to exponential of x. And 1 over I is minus I, so you would say, oh, exponential of x is equal to cosine I of x minus I of sine of I of x. Is that correct? I think so. Okay, that's what it must be correct because we just added these two, right? It should work out. But typically, this is not the way it is popularly written. So let's see how you can.
Why is there is a minus sign?
Oh, is there a?
Cos x plus I is I will cancel the I there. there is a I in sin ix. So in the denominator, I will cancel the I. So
We introduce I square. Negative, negative plus.
This is wrong, you think?
None.
then the next line.
Next line. Oh, next line. Did I mess up? But I just took a I to minus I, right? When I took the to the numerator.
Yeah.
Right.
whatever it is.
This is, maybe the confusion is this is not the way usually it is written. If you might be familiar with a relation, so maybe this is the correct, or I shouldn't say correct or wrong. This is correct, right? This is the popular relation. Is that what you're having in mind? That's correct.
Not exactly. I got this I and I cancel that. And now I get it.
You get it? Okay. So no confusion, right?
Mhm.
Okay. So it's all. Okay. I just went by introducing this cosines and doing this and reaching that. So that's a correct relation, but we can also proceed slightly differently. So let's start with cosine x here. Once you see this, you can actually redo it here itself, but it's more convincing when you do it like this. So start with the cosine x definition and write that as 1 plus I of x, the whole square, over 2 factorial, and plus I of x, the whole raised to 4, over 4 factorial, and so on. Right? That cannot be wrong because I just took it here and I introduced I square here.
I think that should be cos ix.
Oh, I made a mistake again. Yeah, this one?
Mhm.
No. So I start from here,
Mhm.
right? I take this 1
Oh,
minus
yeah,
1 and put an I square. Here, this is 1, I make it I raised to 4 and so on. Right? So, so as it sits, it is true statement. That's all. I'm saying. Similarly, start with sine of x. This time, I don't really do sine of x. I put in an I also in here. So this gives me I of x. So I put in an I. There's a minus 1 there. There are 2 i's. So this is plus I of x cubed over 3 factorial plus the point is, since once I notice this, I'm manipulating this old equations to get something which is more popular. So, okay. Now we see that, oh, if we add these two together, that's exponential. So cosine of x plus I sine of x is equal to exponential of I of x. Okay. That's it. Observation one makes. And that is useful because that's the expression we have here, right? Cosine theta plus I sin theta. Okay. So this becomes a reasonably good, or this is the first step towards understanding that this is actually a representation on the complex plane. That's exactly this. This is called de Moivre's theorem. I'm not sure if my pronunciation is correct. Pretty sure that's the correct way of saying it. But the idea is simple, that cosine plus sine and sine with an I term, that's an exponential of I of x. And now if you come back here, right, on this complex plane, now there is another way of writing this, and that's R times exponential of e raised to I theta. Okay. So again, there is a picture of a complex number, that there is a point on the coordinate plane R and theta that will be represented by complex number in this form. And remember, exponential has nice multiplication properties, right? when you multiply two exponentials, the
At the
argument just adds, so it becomes an addition in principle. And that seems to suggest that when you multiply these two complex numbers, there should be a nice pattern in there. So that's what we will try to see. Any questions on this? So basically the point is that I try to emphasize that cosine theta plus I sin theta is nothing but exponential. That's the only step. I sort of proved it. Any questions? Now we'll start doing more things with this. Okay. So if you have two complex numbers, this is Z1, which is now x1 plus iy1. That's one way of looking at it. If you think of it as vectors, those are the components of the vectors. And this is also r1 exponential of I theta 1. Right, there's a unique theta 1 associated with this complex number. Similarly, Z2 will be x2 plus I2 and R1, R2 exponential of I theta 2. If I were to do Z1 times Z2, this will be equal to x1, x2 minus y1, y2. And plus I times x1, y2 plus x2, y1. So, and that's not very intuitive, right? When you write that, that's not very intuitive unless you have very lot of experience with it. But instead, if you go to the R and theta representation, this is straightforward. You will say this is R1, R2, and exponential of I theta 1 plus theta 2. Now I should emphasize, going back here, that theta is always less than 2 pi and greater than or equal to 0, right? If by any chance it goes more, then you have to cut off the 2 pi, right? It's periodic. That's always there. So this has now an interpretation. So go back to our complex plane. Let's say this is your Z1. So that's your Z1. That means there is an angle theta 1 in here. And there is this length is R1. I'm not writing it to avoid clutter. Okay. Let's say the second one is R2. So let me say this is slightly longer. That's R2, and that's Z2. And this I say is theta 2. Okay. And now, if you want to find out what is Z1, Z2, one way to proceed and calculate this whole thing and find out what that coordinate is. Okay, sure, there's nothing wrong in that. But here there is an easier way of doing this. What's the magnitude? R1 times R2. But before that, let's see what is the direction along which line it is. It is theta 1 plus theta 2. So this is theta 1, that's theta 2. Theta 1 plus theta 2 will be somewhere here. So it is somewhere going to be along this line. That's for sure, right? That's theta 1 plus theta 2. That's theta 1 plus theta 2. Is that clear? I added a theta 1 to the theta 1 to the theta 2. And if R1 and R2 are greater than 1, R1, R2 will be larger number, and this will be Z1 times Z2. This point here. Okay, any questions on that?
So why is the magnitude of Z1, Z1, Z2 is in the left quadrant? I mean, why is it left? If R1 and R2 are positive, then in case then.
But R1 is the length, right? I think it has nothing to do with quadrant.
Okay, so I can place it anywhere. Yeah, I get it.
Correct?
Mhm.
Like magnitude has
Nothing to do with the quadrant. Yeah,
right, nothing to do with
only the angle.
angle. Yeah. First, find the angle along which line it is, and it's a half line, remember? Theta 1 plus theta 2 is a half line. Starting from here, that's the length of that R1 arc. Okay, clear? Question?
If your theta angle is larger than pi,
Larger than I.
larger than pi,
Larger than pi, yes.
then you get like a, like how would you?
Yeah, so
compare?
let's do examples. Right? Maybe how about examples? Yeah. So maybe let's say Z1 is equal to let's keep 1.0 times exponential of you want it greater than pi, right? So 180 degrees. So this is pi converted to what do you say this? I want to work in degrees, but I cannot. Here, by the way, things has to be in radians, right? It's necessary that it is in radians. So you would say it is, how much is that? Pi is 180 degrees, right?
Yeah.
So if I want some angle theta in so this is, let's say theta is in degrees. I put this in here, so this will be what? Pi times pi over 180 times theta in degrees, in a sense, right? So pi times pi. Hold on, I'll get a better example. Let's not go there. That's confusing, right? Okay. Pi over 10 is small enough. Right? Pi over 10 is 180. That's 18 degrees. Correct. So let's have pi over 10 as an example. So it is pi plus pi over 10. So it is 11 pi 10 pi. So that's somewhere here. So this is Z1, and Z2 is, let's say, 1.5 or 2, let's say, 2 times exponential. Now, what is the angle you want to keep for the second one? Let's have pi over 6. Okay. Clear? So where will this be immediately? We say that this is 11 over 10, so it's so this is 1, the circle, and that's 2. 1 and 2. This is 1, and this is about 10 degrees. So that's somewhere here. That's my Z1. Right. And Z2 is on the second circle with 30 degrees. So this is 10. So that's about 30 degrees. Is that clear? Right. So this pi over 6, so 11 over 10 pi is 190 degrees, and pi over 6 is 180 divided by 6, that's 30 degrees. So that's your Z2 and that's your Z1. Correct. Now what is Z1 to Z2 immediately? Z1, Z2 is equal 1 times 2, so that's 2.0 times these two angles added up, that's 220 degrees, right? Or I have to do this, right? 11 by 10 plus 1 over 6. So this is 66 plus 66 plus 10, right? Okay, divided by 60. That's 76 over 60. but that is 220 degrees, right? 220 degrees is about 40 degrees from here. So that's somewhere here. Is that clear? Okay, that's one example, but that's not, I mean, that is surely for the one that greater than pi. I don't know what you had in mind, but there is one thing that comes in. What if your first number was here and you add some number so that it becomes greater than 2 pi, right? So I think that's what you had in mind. So let's do that. This was one example where it is going to be, it's not in the first quadrant. I think you had that confusion, right? So that clarifies that. So let's do another example, Z1. So Z1 is equal to 1.0. And let's have this time big numbers, right? Let's say pi over 2. What is this? What is this equal to, by the way? Let's say geometrically. Anyway, however you want it. That's a very important number. Important complex number, the most important complex number. I, right?
Yeah.
That was the starting point of the whole complex number. That's your I, right? It's on the y-axis, exactly 1 unit there. So that's your I, right? So Z2, let's say, is 2.0, just because it's convenient, and exponential of, let me take something in the fourth quadrant, right? Fourth quadrant. So pi by 4, 1, 2, 3, 4, 5, 6, 7. 7 pi by 4. 7 by 4. That will be 270 plus 45. Right? Because each of this is pi by 4, pi by 4. Right? So that's somewhere here. So again, let's do this geometrically. So that's my one and two. First number is our good number. So that's I. Right? And the second one is here. That's your Z1 and that's your Z2. Right? And now we want to do Z1 times Z2. That's 2.0 times. Now when you do this, e raised to I, 7 over 4 plus 1 over 2, that's 11 over 4, correct? And we notice that, oh, that's greater than 2 pi, right? So any multiple of 2 pi, that's 1. Exponential of I 2 pi is equal to 1. It doesn't matter, right? So I can remove exponential of I 2 pi. So I write this as 2.0 times exponential of I. How do I do this? 2 pi, right? 8. I should get a pi over 4, right? Is this correct? 7 over 4 plus 1 over 2. Huh? 9 over 4. That's, thank you. 9 over 4. So I do this as 8 over 4 pi times exponential of I pi by 4. 1. But this is nothing but exponential of 2 pi. So that's equal to 1. And so this is equal to 2.0 exponential of I pi by 4. And then you know where it is. That's somewhere here. Is that clear?
Yes.
Right. So I think was your question. Good question. Okay. And you see that multi-valuedness, right? This is going to be there all the time, and it is good and bad. Like you will see that there is interesting features in there. Okay. is there any other example? Oh yeah, we should, I should emphasize that so in this complex plane, where is 1? So this is complex plane, right? X and Y. There is 1. It's here, right? So this is 1. That's plus 1. Right? Where is I? That's right here, right? The unit magnitude, that's here I. Where is I square? I square is -1, that's here. And this is minus I. So from now onwards, or I would strongly recommend that whenever you think of I, see that as that vector there, or see that coordinate there. It helps significantly your whole, how do you say, fluency in complex numbers will increase significantly if you start seeing this on the complex plane. Okay, and that's minus I. So for example, I raised to 109, where is that?
So in the same place like here.
Same place, right? That's I, because I raised to 108 is
It's divisible by 2. so
is
that's-
divisible by 4 actually, not 2, right?
Four.
4, because 2 it will flip between these two, right? So this e raised to I, and then, oh sorry, why did I write e? I raised to 1, and so that's one way of seeing this. And there are some homework examples where I ask you to calculate some ridiculously high-powered numbers, but the idea is not for you to go and multiply them. It's actually to see them on the complex plane. Okay, so this is on multiplication. Once we have this idea of multiplication, we can now come back. Now we're going to inverse of multiplication, not inverse really of multiplication. We want to do square root and cube roots. Okay, so okay, so roots. This is called roots, like nth power roots, nth root, right? That's what z raised to 1/3 or something. Let's say z is equal to I. Simple. And we immediately know that this is equal to 1.0 times exponential of I pi by 2. Suppose I were to ask, what is z square root of z? Right. And then this will be equal to I square root of I basically, or better, this is equal to 1.0 e raised to I pi by 2 to half. And that's the same as 1 has unit, square root of 1 is 1. This is e raised to I pi by 4. Okay. And let's see this on the complex plane. And notice the inverse, when we think of square root of z as something, we're asking which number when multiplied with itself gives me I. Right? So I have to reach here, which number multiplied with itself gives me z. So I go back, and this is my circle. If this is pi by 2, exactly half of this, that's here. Right. This is an angle theta. If I multiply this 2 times, I get that, right? And this is unit circle. That's one way of looking at it, and that's of course pi by 4, right? But now that this is a geometrical picture, you ask, is there any other angle that can do this?
Three.
Hmm?
3 pi over.
Yeah, 3 pi 4. So for example, let's say, so now you're in a circle, right? Yeah, that seems to suggest that, yeah, good, right? So here, let's say, so this is your first root, right? That's your first root. That's your e raised to I pi by 4. Let's have another point here, right? Which is basically going all the way here. What is this? Equal to 1, 2, 3, 4, 5 pi by 4. Right? So let's have this as our test root. So we call that ZR. Right? So let's say Z2. Yeah, Z2, right? That's the second root. Let's say ZR. So ZR, a test root, is going to be again 1.0 times exponential of, what did I say? 1, 2, 3, 4, 5, right? 5 by 4 pi. And again, it is using the multiplicity that you guys pointed out that, oh, if you go around the circle, that's also okay. So now ZR square is equal to 1.0 times, I have to do this, e raised to I 10 over 4, right? But that's the same as I get rid of the 8 because that's 2 pi, and that's e raised to I pi by 2 or I. So that's also a solution. Right? So there are 2 solutions now. So apparently this is also a solution. Are there more solutions?
Yeah.
And what are those solutions? Tell me. Okay. 15, right? So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, right? No, 9, right? Why 15? So you would say, let's try ZR is equal to exponential of I 9 by 4 pi. Correct? And you will say that, oh, ZR square then is 18 by 4 e raised to I 18 by 4 pi. But then 16 by 4 pi I can remove because that's 4 pi. And this is equal to e raised to I pi by 2 again. That's good. But then you would say I can remove my 2 pi here itself. Right? So this is also equal to exponential of I pi by 4, which is what we began with. Right? We found we found that root already. Right? So this is just multiplicity. So this is the root. There is of course another root, but that's multiple of itself in the sense angle is not unique. So there are only 2 roots actually. There are rest of them. So if you want, what is your ZR? What are the roots? E raised to I pi by 2. And I can always add I raised to m2 pi, where m is any 0 plus or minus 1 plus or minus 2 and so on. That's trivial. There is another root, which is e raised to pi, 5 pi over 4 times e raised to I m2 pi again, where m is equal to 0 plus or minus 1, plus or minus 2, and so on. Right? Can we get these two roots nicely without looking at this picture? Okay, suppose I were to give you some random number, is it possible to get that? And yes, of course, you can. Okay, so let's okay. So let's say in general we have C equal to, let's keep it of 1, I mean magnitude 1, so that we can be on the circle. That's not really, it doesn't lose any generality so much. So let's say this is 1.0, but this is some arbitrary theta. You have a question? Worried?
Oh, I was, this, you have pi over 2 on the top one.
Oh, this is pi over 4, so this is my bad. Yeah. So we said this is, yeah. But this one more we kind of played around, right? We didn't actually go through an algorithm. So we kind of guessed, oh, I know that this one should give me 2. Then I use geometry to, I use some tricks, geometrical visualization to get that. But algebraically, how do you proceed? So let's say this is Z. How do I get square root of Z? Right. First thing I say is that given Z, I know that this is not unique. There is more to this, and that's I m to pi, where m is 0, plus or minus 1, and so on. That's the same number, right? So I should recognize that to begin with. And then let's say square root of Z is equal to, now do the whole thing, 1.0 e raised to I theta, e raised to I m to pi of. This distributes into all 3. That stays the same. We chose this to be a simple coefficient so that the square root comes out cleanly. And this is I raised to theta over 2. Now, this is e raised to I m pi. Correct. And that's it. And again, we should remember that m is all the way there. So many of them, but only 2 of them will be unique in this case. Okay, always. So actually, is there a way to see that? Let me see. Yeah, so let me put this as exponential. So let me say this is exponential of I theta over 2. That's surely a solution. That's the case when m is equal to 0, right? That's one solution. The next one, when m is equal to not a plus or minus 1, when m is equal to plus or minus 2, that's gone, right? We don't have to worry about that, right? Whenever it is plus or minus 2, that starts repeating. Right? So if I were to not worry about that, so then there are 3 remaining. So that is e raised to I. So this is 1. Right. And the second one is 1.0 e raised to I pi by theta over 2 plus I pi. And the third one is I theta over 2 minus I pi. But that seems to suggest that there are 3 roots, but that cannot be the case, right? Oh, that's because these 2 are the same, right? Right, these 2 are the same. So there are only 2. Is that clear how I mean, I kind of argued this out. So that is plus or minus 2 pi, q plus or minus 3, and so on. We are doing square root. If we are doing square root, this will always be 2 pi. This one will be the same as this, because I'm adding 2 pi's to that. So I don't have to worry about the rest. Right? So I can stop here. And then I say that, oh, plus and minus 1 are the same because one is plus and one is minus 1. So there are only 2 roots, and that's this. So it is only this. So find, pretend that m is not there, m equal to 0. Do this and add a pi to that. That's your 2 roots to that. And we did see that, right? There is 1 root is here, add a pi to that, and that gives me the second root. So this is equivalent to doing your plus or minus, right? We do plus or minus 1 whenever we have 4, right? But this is a generalization of that. So if it was a real number, if this was 0, that's your plus 1. So if theta was equal to 0. So if theta was equal to 0, then square root of z is equal to then 1.0, and this is 1.0 u raised to pi, which is equal to plus or minus of square root of z, right? Plus or minus 1. That's only if it is real. In general, you do the theta over 2 and then add a pi to that. So that's the more general statement. Okay, clear? Questions on this? That's square root, cube root, right? Next is cube root. We did square root, that's your cube root. Let's have first an example, 1.0 exponential of why exponential? Simple, right? Let's do 1. That's it. What's the cube root of z? Cubing what gives me 1? 1 surely, right? 1 is surely an answer. What else? Is that the only solution? Is minus 1 a solution? Minus 1 cube is not a plus 1, right? So I should do ZR, like the root of this. No, what did I say? Yeah, Z cube is equal to 1. What's the answer? Yeah. No. Yes, this was the answer I was writing here. What is this? Yeah, that's fine. That's a Z of R. That's your root. If this is your Z of R, what are the solutions possible? Z of R can be equal to, so that means Z of R cubed has to be equal to 1.0. And we're asking, what are those numbers when cubed give you 1? And of course, Z of R is equal to 1.0 is surely correct. Right? But are there more? So again, let's look at this diagram now, right? You're on a unit circle, that's 1, so it's convenient. We want to reach here by going 3 times in 3 steps. we want to start from a number and go in 3 steps and reach here. That seems to suggest that divide 360 by 3. Right, 2 pi by 3, 360 by 3 is 120 degrees. So it seems to suggest that if I were here, whatever this angle is, 120 degrees. If I go 2 times, I'll reach here, 3 times I'll get here. Right, so it seems like e raised to what about z of r is equal to exponential I 2 pi by 3. Because if I cube it, 3 will go away, e raised to 2 pi, that's 1. Right, so z cube is equal to 1.0. Right, so that's also correct. That's indeed a solution. Right? Is there any other solution?
I think those could be only 2 unique solutions.
No, 3.
That should be 3. Yeah.
3, yes.
So
So
three.
in general, nth power always has n solution.
Oh.
Yeah, any polynomial always will have n solution. So you want to keep trying?
72.
272. 272 will be here. I know the answer, so it's not that. So the key is the following. I started with 1, right? So that was here. I want to reach here. This is, first of all, this itself multiplied by 3 times 0, 0, 0. That's 3. Next is I can reach here in 2 pi, so 2 pi divided by 3. The next circle is 4 pi.
4 by 3.
4 pi divided by 3. And what is 4 pi divided by 3? 4 pi is 367, 20 divided by 3,
240.
240. So that's here, right? So that's somewhere here. So the idea is this is 240. When you do another one of 240, you will get here, and then the third one will get here. Is that clear? So the point is ZR is equal to e raised to I 4 pi over 3 is the next solution. Or you can also see this as a minus 2 pi over 3. That's of course okay. So again, do ZR cube 9.0, that's okay. Next one, I don't care because they will start repeating itself. Like that 6 pi over 3. 6 pi over 3 is also a correct solution, but 6 pi, 6 pi over 3 begin, that is just this one, right? That's just this. 8 pi over 3 will be the same as this. 10 pi over 3 will be this, and then you start repeating itself multiple number of times. Can we see this algebraically? What if I did not use the geometry picture in here? So what I would do is I start from z. So z is equal to 1, but then I say 1 is not, I can have any m 2 pi. Right? That's all ones. There are many ones here. M equal to 1, m equal to 2. Any of those is 1. M is 0 plus or minus 1 plus or minus 2 and so on. Z, third power of z, third root of z, this is equal to e raised to I 2 pi over 3 times m, right? That's your roots, right? Where m now is equal to 0, plus or minus 1, plus or minus 2, and so on. That's all your roots. But only 3 of them are independent. So that's it. So if you write it in the exponential form, it comes out immediately. So just for want to clarify this more, so this is e raised to I0, this is e raised to I2 pi by 3, and e raised to I4 pi by 3, and then repeats and repeats. And this was, so just to give you a historical picture of this. Yes, please.
It can be -1 and -2.
Here,
Yeah,
this one?
Yeah.
-1 and -2.
It can be.
Oh, it can be, yes,
Okay.
because it is -2 pi by 3. If it is -1, then this will be -2 pi by 3. That's exactly this point. Right? -2 pi by 3 is the same as this. That's one point.
Oh, I see.
Correct?
Yeah.
The -2 pi by 3 is the same as this. So after a while, it starts repeating itself. So there's independent ones that are only 3. That's what and repeats. Right? That's what good, good. Any other observations? Yeah. Now we have 4 minutes instead of doing anything else. Of course, you can do z1/4, right? Right, 1/4 is again, you just, I mean, if you start from here, it's just 3 steps. But have the geometrical picture, it's very, very helpful. But algebraically it is there, but then you're always confused, or did I miss this, or did I get this -1? Is it unique? There's always a confusion there because it's a if and it's a trial and error. So here's a historical picture. This is how in 1550s. So if you have, so suppose you have a cube root, right? So this is, we're talking about 1550s. Or like 16th century. So if you have any cubic equation, x plus d equal to 0, like a quadratic equation, you would like to solve for that. And it is by moving the, I think this we talked about earlier. So this is having a plot like this. Move this point to the origin, and always this can be converted into a form px plus q. By change of coordinates, you can convert any cubic equation into this form. Mostly, basically the idea is move that origin to here. So if you can solve this equation, you can solve any cubic equation. Okay. And until 1550s, they didn't have such a solution. Okay. And then came Cardano or Italian guy, and he gave the following solution. He did, just by trial and error, he found that the following solution helps, right? So this is -q/2. And PHYS, right? Read about this story. Read about Cardano. It's a very nice. So there was a rivalry between Cardano and I think it was I can't spell it. It sounds like tortilla. No. Something starting with TOR, like tortilla. Yes. Butcher it. Yeah. But there was a rivalry between them. Yeah, let me tell it in 15 seconds. Like one of these guys, in those days, you don't publish, right? you have competitions, like you have basically a real, in public, you will come and say that, okay, ask me any question. And this is in a real court, like King's court. There will be two intelligent people sitting, and I'm the brightest person, I can solve anything. You can ask any question and you will solve it. Okay? And so this was one of those problems where no one could solve it. And one of them came and said that I can solve it. And he cheated in the sense he didn't have a solution. He said that I can solve it. And okay, next day you go and you have to find out, right, if you can solve it. But he did not know how to solve it. But once he knew that this has a solution, overnight he found the solution. Right, that's a story. So he came up with the solution overnight simply because someone else said that there exists a solution, even though the other guy did not have a solution. This is like the homework problem, right? Homework problems are easy to do because you know that that's solvable. When you go to the research problem, they're much simpler problem, but you don't know. Maybe it is unsolvable. Why should I try? Right? So you don't even try it, right? So something like that. So this is quickly. Let me finish this. Square over 4. But yeah, quiz is to read about that, right? Cube, I think. Yeah, cube over 27. So he came up with this solution, but it has this 1 over 3. That's the point. Okay. And oh, there's a square root here. So. Okay. Now, so this is okay. So you, looking back in time, except for the stories, you said, okay, that's a formula. So what's the big deal, right? But it is interesting in the sense, for example, if you do the following: x cubed minus 15x minus 4. This, if just by trial and error, you can check that x is either 4 or it is minus 2 plus or minus root 3. Okay. And this is, let's say you are not aware of complex numbers, especially this 4. Right? But if you were to go back and put this formula, they're complex numbers. The solution has a complex structure, but the answer is 4. So how do you have an formula which has a complex structure, which has complex numbers in it, but it is practically 4? So it seems to suggest that a real number has a complex, a sum of 2 complex numbers. And what's happening is that if you look at it as a complex, this 4 is sum of 2 numbers like this, right? It can be this, or there are many such structures, right? If you add these 2 complex numbers, you'll get here, right? Or actually, I should make it smaller. Right? You'll get here. So 2 complex numbers can be a real number, and that bothered people a lot. How come this is a real number, but when I use Cardano's formula, I'm getting complex things, and what does this mean? And they struggled a lot with this. It was not clear at all. So read about that. That's a quiz, right? It's kind of interesting. So, and did this get recorded? Yes, I think so. Yeah. Okay, good. You guys have a class, right?